I work in the field of machine learning, and I'm going to tell you about some of the exciting developments that are happening in this field. And really, it's all about dealing with uncertainty, which is an interesting problem for computers, because computers fundamentally, as you all know, are very certain things, in the sense they're based on logic. Everything is 0 or 1, everything is true or false. It's completely certain. And yet the world in which computers operate, the data that computers have to deal with, is full of uncertainty. So let's have a little look at some examples of what I mean by uncertainty in the context of computing. So here's a picture of an object, in this case an animal, a llama. And one of the things that we want to do with images sometimes is to cut out the objects or remove the background. And in this case, we might try to solve the problem by looking at colours. So the difference between a foreground object and a background often lies in colour and texture. And the problem with this particular example, of course, is the animal's quite well camouflaged. There's a great deal of uncertainty about which is foreground and which is background. And yet we need to address that uncertainty if we want to remove the background. We'll come back to that in a moment. Here's another example that we'll also return to. Two people are going to play chess. Which person is going to win the game? Can we predict the winner? Again, it's full of uncertainty. We might know that one player is stronger than another player, but it doesn't mean that the stronger player will necessarily win. So again, there's uncertainty. Here's a very practical example. This is a web page. It's a page of search results from Microsoft's search engine, Bing. And somebody has typed in LCD into the search box, and here are some search results. The first one is a Wikipedia page, and so on. But also, we have these other links, and these are advertisements, and that's how search is paid for. So the model is that advertisers bid in an auction to have the advertisements shown alongside the search results, and they bid against these keywords. So people who are interested in selling LCD televisions, for instance, will bid to have their advert shown against a search like LCD. And if they win that auction, then their adverts get shown. And if the user, you, searching for something, if you click on one of the adverts, then the advertiser pays money to the search provider, in this case Microsoft. And of course, if you click on the Wikipedia page, for example, then no money changes hands. And the fundamental problem we have to solve is to predict where somebody is going to click. Or put it another way, we have to work out the probability that somebody will click on a particular advert. It's no good showing somebody's advert. They could bid $1 million to have their advert shown. If you keep showing their advert and nobody ever clicks on it, you make no money. So the fundamental problem is a problem of uncertainty. It's about where people are going to click. So being able to make accurate predictions, the probability that somebody will click on a link is the foundation of the search business, and that's a multi-billion-dollar business. And here's a final example, which I won't have time to discuss in detail, but this relates to my own research, which is the problem of trying to understand asthma. Now, asthma is the largest chronic disease of childhood. It's growing in prevalence. Nobody really understands what causes it or how to deal with it effectively. Asthma, we know, has genetic factors that influence it. We know it's influenced by environmental factors, growing up with furry animals, being allergic to peanuts, and so on. But the relationship between these is very unclear at this point. We're taking the same kind of machine learning techniques that we use in the case of Bing to choose which advertisements to show, or in some of the other applications that I'll show you. We're taking that same mathematics and we're applying it to try to understand the causes of asthma. We're making some very exciting progress, and this is being done in collaboration with our colleagues at the University of Manchester. So these problems, and many problems, in fact I'd say most problems that computers have to deal with today, involve some kind of uncertainty. And yet, as I said at the beginning, computers are based on logic, so we've got a bit of a challenge. How do we get a computer that deals with ones and zeros to address real problems that involve this uncertainty? So what we need is a kind of calculus of uncertainty, a mathematics for dealing with uncertainty in a way that's principled, in a way that is optimal, so that we can make the best possible decisions even though we're faced with uncertain information. So to introduce the idea of the mathematics of uncertainty, I'm going to show you a little demonstration. So this is taken from the Royal Institution Christmas Lectures in 2008, and these are on a DVD, which I think is in the pack that's being handed to you. This is one of my favourite demonstrations. It's called a Galton machine. It goes back a couple of hundred years or so, but it's still a great demo. So I hope you can all see this. Can we bring a camera? Can we put a camera on the screen? We can't. Okay, I hope you can all see this. What we've got is a series of pins arranged in a kind of triangular pattern, and then under the pins we have some vertical slots. Now these are just BB pellets. Now, if I put one of these pellets into the machine, it bounces off the pins and then it lands in a slot. So I'll put another one through, bounces off the pins, it lands in a different slot. Now, this process of bouncing around off the pins looks very random. In fact, it is random. You really cannot predict which slot a particular bead will land in. So this is a situation in which we have to deal clearly with uncertainty. But it doesn't mean that mathematics is hopeless and we give up and go home. Far from it. So to see what I mean, what I'm going to do is pour a large number of these pellets into the machine, and we'll see what happens. So if you imagine trying to predict where a particular pellet would land, it would be impossible. Okay, so I think you can begin to see a bit of a pattern building up here. Okay, so you can see that there's clearly a pattern has formed. Even though each bead is unpredictable, we can't predict where a particular bead lands. If we look at a large number of beads, they form this very well-defined pattern, and it's sufficiently well-defined that I'm able to predict in advance what it's going to look like. And you can see that's a pretty good fit. And this is called a Gaussian curve or a normal distribution. And so the height of this represents the probability that a bead will land in that particular slot. And in fact, we can work out the shape of this curve in advance. It has a very simple mathematical formula. So probability theory is a branch of mathematics which allows us to make very precise statements about things such as this, which are uncertain. And we use that branch of mathematics as the foundation for modern machine learning. So I'm going to show you some applications, but before I do, I just want to have a little think for a minute about what those probabilities really mean. So the usual concept of probability, the one that we first learn about in school usually, and the one that was illustrated over there, is what's called the frequentist view. That's the idea that probability is the frequency of occurrence of repeatable events. So a simple example is flipping a coin. If I say the probability of a coin landing heads is 50%, what that means is if I flip a coin a very large number of times and count the fraction of times it lands heads, that fraction will tend towards a half as I do more and more trials. That's the frequentist idea of probability. We're going to use probabilities in a much more general sense. It's called the Bayesian framework, the Bayesian view of probability. So Reverend Bayes was an English clergyman, and 250 years ago, he provided a rather different interpretation of probabilities as a way of putting numbers to uncertainty. So let's say I ask you, is it going to snow tomorrow? You can't be certain whether it will snow or not. You're uncertain, but because of all the weather patterns, you might think it's reasonably likely. And you can put a number on that. You can say that I'm 70% confident that it will snow tomorrow. Or in the middle of July, you might say there's a 1% chance of snow tomorrow. So let's have a little example to sort of illustrate this difference, because it's very important. Imagine I've got a coin, and the coin is bent. And if I flip the coin a large number of times, then let's suppose I measure this, and I measure that 60% of the time it lands with a concave side upwards, and 40% of the time it lands with a concave side downwards. That's just the physics of this bent coin. Now suppose you can't see the screen very well, and you don't know which side of the coin is heads and which side is tails. You know it's a bent coin, you know that 60% of the time it will land concave up, but you don't know which side is heads and which side is tails. So if I asked you, what's the probability that when I flip this coin I'll get a heads? What would you answer? Any answers? Somebody said it? 50%. Right, and that's the correct answer. That's your best answer, 50%. It doesn't mean that if you flip the coin millions of times, that half the time it will land heads, half the time it will land tails. It means something very different. It means if you flip the coin many, many times, you know that either 60% of the time it will be heads, or 40% of the time it will be heads, but you're not sure which. So the 60%, the fraction of times it lands concave side upwards, is a frequentist probability. But your uncertainty about which side is heads and which is tails is a Bayesian probability. It's not something you can repeat many times. The coin either is heads on the concave side or it's tails. You can't repeat that many times. It's just a fact. But you don't know what it is. So that's the idea of Bayesian probability. And that's the foundation for modern machine learning. So let's have a look at an example of something that we can do, a little demonstration of something that we can do once we know about the theory of probabilities. So this is a little example called, we call this the movie recommender. So each of these little icons represents some well-known film. What we're going to do is I'm going to teach this about my preferences for movies. So I'm just going to pick a film that I like. I'm going to drag it across into the green region. So what I've done is I've told the system that I like that particular movie. I've watched that movie, I like it, and I've rated it as green. I like it. What the system is doing is taking that information, it's combining it with the ratings that have been given to these films and many others by hundreds of thousands of people. So actually tens of millions of ratings have been given to many, many different movies. And it's comparing my patterns of likes and dislikes with the patterns of likes and dislikes of other people and looking for similarities. And on the basis of those similarities, it's trying to work out whether I will like some other movie that I haven't seen. And what it's doing is it's the vertical position on this slide is irrelevant. It's just there to space things out so you can see them. The horizontal position represents probability. So a movie that's on the right-hand side is one which the system is very sure that I will like. A high probability that I will like that movie. One on the left-hand side is almost certain that I won't like it. And one's in the middle, it's completely 50-50 whether I will like that movie or not. So at the moment I've told it very little information. I've just said I like that particular movie, and you'll see all these other movies are sort of clustered around the middle. So I've given it very little information, so it's really not very sure whether I'm going to like these movies or not. So what I'm going to do now is just give it some more examples. So let's say I don't like that movie. And what you see is the movies are spreading out. They're moving towards the sides. So the probabilities are going, instead of being more like half, they're being more like 0.1 and 0.9. There's a reduction in uncertainty. And that's what it means for machines to learn from data. As they see more data, their uncertainty is reduced, and therefore they've learned something. So let's carry on. Let's give it some more movies. So I like that one. I don't like that one. And you can see, even after just 4 ratings, these movies, instead of being clustered around the middle, are being pushed out to the sides. So there's a big reduction in uncertainty. It's learned a great deal, even from those 4 examples. Nothing is completely up against the edge. It's not completely certain of anything. But nevertheless, this is very useful. If I'm going to go out and rent some movies, I should pick ones perhaps down the right-hand side rather than the left-hand side. Okay, let me just show you one last thing with this demo. Let's take a movie down the right-hand side. So this is a movie which the computer is pretty sure that I'm going to like. And let's say I watch that movie, and it turns out I like it. So I'll drag this across here. Watch what happens when I let go of the mouse. Tiny little change. Okay? It thought I was going to like that movie. I said, yes, I do like that movie. There's very little surprise, very little changes. Let's take a movie down the left-hand side. Let's say there's one of these movies. These are movies which the system is pretty certain that I won't like. What happens if I watch this movie and I say, actually, yes, I do like that movie after all. Now watch what happens. It's a huge change. That's because that result is very surprising to the system. It's a basic result of the mathematics of probability theory that information is precisely the degree of surprise. So in that second example, there was a huge surprise in that result, and therefore there was a huge amount of information conveyed by that data point. The data point from the right-hand side conveyed very little information. Okay, so this is a little illustration of what we can do with probabilities. So let's have a look at another example. We'll go back to that image problem that we discussed at the beginning. So imagine that we have images with objects in them. We want to cut the objects out in order to paste them into other images, for instance. Well, the difference between the foreground and the background, between the object and the background, lies largely in the color differences. The foreground have different colors to the background. And The problem then we have to solve, we're trying to find which is the foreground and which is the background, and we can use the colours to help us do that. Now, if somebody told us the colours of the foreground or the colours of the background, it'd be quite easy. We could go through every pixel in the image and label it up according to whether it belongs to the foreground or the background. The problem is we don't know the colours. We don't know the colours because we don't know which is the foreground and which is the background. So we've got this kind of chicken and egg situation. Okay? If we knew the colours, we could work out the foreground. If we knew the foreground, we could work out the colours. So what we're going to do is we're going to make a guess. We say we'll guess that the stuff in the middle is most likely in the foreground. Maybe the stuff around the edge is most likely the background. That will give us a guess as to the colours. We can use the colours to make a better guess for the boundary of the object. We can use the better guess for the boundary of the object to make a better guess for the colours, and so on. Now, that works okay. It doesn't work brilliantly. This is what would happen if we just used that colour information. So what we've done here is to tell the computer the colours of the foreground and the colours of the background, and we've asked it to, what we call this segmentation, find the boundary of the object. And it's sort of done an okay job. You can see pixels in blue are pixels which definitely belong to the foreground, pixels in red definitely belong to the background, and the shades of grey in between are intermediate values of probability where the computer's uncertain. And you can sort of see the shape of the animal, but it's not done a great job. There's lots of regions of black here. There are bits of blue out in the background, bits of red in the foreground. So it's sort of not a bad attempt, but it's not good enough for a practical application. We need something else. And this is another fundamental point about the way computers can learn from data. They can learn for themselves to solve problems. They don't just learn from data. They learn from data plus other information. We call this prior information. And we can see what it is in the case of an image by imagining, we zoom right in as we see the individual pixels. So each of these squares is one of the pixels of an image. Now imagine somebody had labelled up an image with blue as foreground, red as background, with the true answer. What would it look like? Well, it wouldn't look like this. Okay, real images wouldn't look like this, where pixels are randomly assigned to foreground and background. They're all jumbled in together. Real images don't look like that. Real images, we have big regions of foreground and big regions of background, the sort of smoothness property. So it looks much more like this, where we've got big regions here of background and big regions of foreground and occasional boundaries between them. So we call that prior knowledge. So we have to combine this general knowledge that we have about all images, all natural images, we combine that with the data from a particular image, and that allows us to do a much better job of pulling out the foreground from the background. So let me show you a little demonstration of that. So here is an image of an object. Again, it's an animal. So I've selected the I select the image, I go up to Picture Tools, I click on Remove Background, I keep the changes, and in 3 key clicks we've managed to segment the object. We've cut the object away from the background. This demonstration is simply the current version of Office. This is Office 2010, and this background removal tool was developed by the Computer Vision Group here in the Microsoft Research Lab in Cambridge, and I'm showing this to you in the context of PowerPoint. And the purpose of this is to enable people to do image editing, cut objects out of images, in a way that's very quick and easy. So not aiming for absolute perfection. What we're aiming for is to do it very quickly, very easily, get a pretty good result, and not have to have a tremendous amount of skill to do it. So let me show you another example. So that was an easy example. Here's a slightly harder example. So again, we'll remove the background. So I go up to Picture Tools and click Remove Background. We'll go through a little bit more slowly this time. What it's done is it's put down a rectangle into the image, and it's guessing that the foreground object is inside the rectangle and everything outside is background. Now that's not quite true for this image, so you can see it's not done a particularly good job so far. Its initial guess is that the blue clothing and the blue ocean belong to the foreground, and everything else which has been turned pink, so it'll be the sandy colours and the flesh colours, all belong to the background. So the first thing we need to do is just give it a better hint as to where the object is located. All we'd have to do for that is just move this rectangle so that it bounds the object a little bit more tightly. And now you can see it's done a very much better job. It's still not quite perfect, because it's still kept a little bit of sand here in the foreground. So what we're looking for is a system that's as automatic as possible, But because images are so complex and so variable, a system can never be fully automatic. So what we also have to have is a very quick and easy way of making corrections. So what we're going to do is remove that sand by just clicking on this button, which is Mark Areas to Remove. And then we'll just go down here. All I'm going to do is just sweep the mouse through that region, and it disappears. And I can do a copy, and we can go to New Image, do a paste. And there she is. I'll make her a bit smaller, put her on the path. And that's it. So cut and paste in about 5 or 6 key clicks. Another nice thing about this is because we actually have the cut-out shape of the object, because we know the shape of the object, it's then trivial to just throw down a little shadow into the scene, and then it makes it look much more natural, like she really belongs there. Okay, so that's background removal in Office. So again, another example of the use of probabilities. So what I've shown you so far are some nice examples of machine learning, of computers dealing with uncertainty, dealing with uncertain information, using probabilities, and learning from data and applying that technology to some interesting applications. But really, we're just scratching the surface of what we can do with machine learning. And some very exciting developments have been happening over the last 2 or 3 years, to the point where I'm now convinced that the next 10 years are going to be the golden age of machine learning. So over the next 10 years, we're going to see many, many more applications of machine intelligence and machine learning of the kind that I've described. And the reason for this is because of something which is sometimes called the data revolution. So you'll see a lot of articles and discussion about this, and phrases like data is the new oil, a sort of recognition of the increasing importance of data. And one of the reasons there's an awful lot of it, one very careful survey in 2007 concluded that the total amount of data stored in the world back then was 280 exabytes. An exabyte is 1 billion gigabytes, so that's a lot of data. But more than that, it's growing, it's doubling every 18 months. So it's growing rather like Moore's law, like the number of transistors on a piece of silicon, it's doubling every 18 months. So it's growing exponentially. When something's growing exponentially, it's growing in a very dramatic way. Now, people talk about explosive growth. This is much more dramatic than any kind of explosion, because every 18 months we get as much data as we had at the end of the 18 months. We have as much new data as we had in total at the start of the 18 months. We'll put it another way, which is what, December. So by June of 2012, the amount of new data in the world collected or created between now and June 2012 will be equal to the sum total of all the data ever collected from the dawn of humanity up to the present time. Right? That's the meaning of exponential growth. It's really breathtaking. And it's not just that there's an awful lot of data in the world, but it's being collected and stored in rather different ways. This is what's called cloud computing. I'm sure you've come across this. So we're seeing a big shift in the nature of computation from standalone computers, that is, computers which live in your hand or live on a desktop and just operate independently, to computation which lives in vast data centers, huge warehouses full of hundreds of thousands of processors and lots of storage. So the data is being stored in these data centers, the computation is happening in these data centers, and we're accessing that over the internet. So that's the cloud computing revolution. We're seeing a shift from software providing applications, that is sort of an application that stands alone and runs on your laptop computer or whatever, to the use of software to provide services that are delivered over the internet from the data center, and increasingly data-based. And data sets are no longer isolated. You no longer just have, I've got my data set on my computer and you've got your data set on your computer, and they're not connecting to each other anymore. Instead, they're all hooked up together because all the data resides in the data center. So we can do very interesting things by combining data from one source with data from a different source, things which wouldn't be possible with one kind of data alone. So a rather simple example would be, you're walking down the street in Cambridge, interesting looking college, you take a picture with your mobile phone, the image goes up to the data center, it's combined with information from lots of other images, it does some image search, it might combine it with GPS and cell mast information from the phone, all this data is being fused together, it's then fusing with other data, information about the nature of the college and so on, and then a few seconds later, back to your phone, it says, this is King's College Chapel, it was built in such and such, and the nearest Starbucks is 100 meters on your right, that sort of thing, okay. Something else we can do with data fusion is what's called personalized healthcare. So imagine a world, which may not be very far away, in which many, many people, millions of people, have all their electronic health records stored in a data center. And imagine a world also in which it becomes very cheap to sequence the genome of an individual person. So that the day when for $1,000 you can have your entire DNA sequence is probably only a few years away. Well, the combination of all that genetic information, that environmental information, those medical records, all fused together will allow us to do an entirely new kind of medicine. Really understand the influence of environment and genes on all kinds of diseases in a way that was completely impossible before. So there's a huge amount of excitement about this personal healthcare revolution where we can combine all this data together and then deliver healthcare information back to you as an individual that's highly tailored to your genetic profile, your environment, your background, and so on. So a lot of excitement about that as well. And then finally, and perhaps most importantly for this talk, we're seeing a transformation in the nature of software. Software from handcrafted software, where somebody says, I'm going to build a word processor. And they sit down and they design all the software, and at the end, when they run the software, you've got your word processor. That's kind of a handcrafted solution. Increasingly, solutions are not being handcrafted by people dreaming up algorithms and ideas in their head. Rather, they're programming the computer instead to learn from experience, and then the solutions are being learned from data. So we don't try to program the computer with rules that work out whether you're going to like a movie or not. Instead, we just show lots of movies to lots of people and see which ones they like and which ones they don't like, and we build a movie recommender system based on all that data. So this is a very exciting revolution, and we're just at the beginning of it. I'm just going to finish with one last case study, which gives you a little glimpse of the sorts of things we can do in this new world. So again, this is going to use Bayesian probabilities, and it's to do with the problem of ranking. So ranking means sort of putting things in order. It's a very common problem. It arises in lots of different places. Here's a simple example, which is playing games. So let's take the game of chess. Let's imagine that we're all members of a chess club, and we play games of chess against each other. And what we'd like to have is a kind of leaderboard. We'd like to know who's the best chess player, who's the second best, and so on. And then we can all compete to get as high up the leaderboard as we can. Now, there's a standard solution to this. It's been around a very long time. It's called ELO. Now, ELO is actually the name of the person who invented it. It's not an acronym. And it's like it's a frequentist technique, that old style of probability theory that I mentioned before. And what it does is it maintains a strength value for every person. So you might have a strength of 130, you might have a strength of 140, and so on. Everybody carries with them a number which is their strength at chess. And this system, by the way, is used internationally, worldwide, in chess and in many, many other games. It's the standard system. Now, what happens when two people play a game of chess? Let's say you're 130, I'm 140. We play against each other. Let's say you win. Right? You're the weaker player, but sometimes the weaker player will win. There's no certainty here. There's a little formula in ELO which will increase your score a little bit, decrease mine a little bit, so you'll become 131, I'll become 139, and then we go off and we play the next game. And so by all these tiny little changes, people's strength values, estimated strength values, change and evolve as they play more and more games. So that's ELO. And there are some problems with ELO. For instance, it can't handle team games, nor can it handle games in which there are more than two players. So what we've done is to replace ELO, this frequentist system, with a Bayesian system, which we call TrueSkill. And it solves these problems of having teams, of having more than two players, but it also does something that's actually much more dramatic. This shift from frequentist to Bayesian allows us to do something very dramatic, and I'm going to show you with an example. So this is a game for the Xbox. It's called Halo. Has anybody here ever played Halo on the Xbox? Wow, that's a staggering proportion of people. Right, okay, you know what I'm talking about. So what we did is we took some data from Halo, from the Xbox, and we analyzed it, first of all, using the old-fashioned ELO system. And there are hundreds of players in this data set, but let's just look at two of them. So there's the red curve and the blue curve. These are two of the players, and this is what happens as they played games of Halo, not just against each other, but against all these other players. Along here is the number of games they've played. So this goes from 0 up to 400 games. Right? So these people are burning up a serious amount of time on this. And up here is the system's estimate of how strong they are at this particular game. And everybody starts off at 0. And as they play games, you can see that their strength values are evolving. It's using exactly the same algorithm as used in, this is ELO algorithm, exactly the same as used in chess worldwide at the moment. If we take the same data and we analyze it instead using our Bayesian system, we see a dramatically different result. we see a much more rapid convergence of the estimated strength value. And so rapid in terms of the number of games played. So you see after 100 games, under ELO, the strength is still evolving really quite significantly. It hasn't converged at all. Yet after about 10 games, under the same data, it's much, much closer to convergence. So what this means is you can play far fewer games for the system to get a really good estimate of your true strength value. So we call this the true skill system. And so that's a huge advantage. And it's for that reason that when, back in 2005, when Microsoft replaced the Xbox with the new console, the Xbox 360, it switched from using ELO to using our TrueSkill, Bayesian ranking system. And so TrueSkill is now used for ranking on all Xbox 360 games. So if you play on the Xbox 360 on Xbox Live on the internet, then this is the system that's used to do the ranking. And it operates on a very large scale. We're about 24 million active users at the moment, playing millions of matches per day, and all that data is being analyzed in the data center 24 hours a day, 7 days a week, analyzing people's strengths and working out those leaderboards. But it's used for something much more important, in a sense, than just those leaderboards. It's also used to work out who should play against whom. If you want to play a game on Xbox Live, you say, I'd like a game of whatever, and in the next few seconds, the data center is going to match you up against other people around the world who have similar strengths. Similar strengths so you can have an enjoyable game, a sort of closely matched game. Now, if it takes you 100 games before the system knows how strong you are, it's a long time before you're getting good matches against people of a similar skill level. If we can do that after just a few games instead of a few hundred games, then we can give you a good experience much more quickly. And that's good because that helps you to keep paying your monthly subscription, so that's important. Okay. So this is, I think, one of the first, possibly the first, what I call a planet-scale application of these Bayesian methods. So previously, we've been using these techniques on applications of the kind I've shown you already, small-scale applications running on a local machine, but now we're using them on a planet scale, processing millions of data points per day. And as I said, I think this is just scratching the surface. I think the next 10 years, we'll see many, many new technologies develop using machine learning. And with that, thank you very much.